Hi class, I'm going to go over a couple of things. First of all, there are a couple of corrections on the flashcards, which I will delineate in an email that I'm going to be sending much later tonight. Secondly, there are two typographical errors in there that I will give you. You should be doing flashcards through 12. It's kind of like the middle of page 12, and I'm going to announce that tonight as well. Another thing, in my list of material for this exam, I neglected to put in the wittig reaction and possibly sodium borohydride, but I think that's in there. You are responsible for all material. The list is there just to help you go through the material. You are responsible for all material in your notes except for carbohydrates and amino acids as I described in class. And I believe it says on the bottom of the list that if I neglected to put something in, you're still responsible for it. You're responsible for what we do in class. Okay? And so there's really no question about what's on the test. The list was just something to help you organize your thoughts. That's all. Okay? So I promised I would do a quick method to get to carbohydrates. I gave you the long method a week or so ago. So if I have a sugar, for example, supposing I have this sugar. Okay, how do you know it's a sugar? Because it's a polyhydroxy aldehyde. Or it could be a polyhydroxy ketone. All right, now, the first question would be, what kind of sugar is this? You might say, how do you figure this out? What you do is you look at what is called the configurational carbon, which is the last carbon in the Fisher projection. If the OH is to the left, it's an L sugar, which is an unnatural sugar. If it's to the right, it's a D sugar. Now, supposing the problem was draw beta D, the beta D version of this sugar, okay, if that's your goal. Remember, the alpha and beta have to do with the anomeric carbon. This is the anomeric carbon, this is the configurational carbon, okay? Supposing the job is to draw the beta D. This means that I want to draw a D sugar, and I think most people should learn how to draw D sugars because you can generate L sugars very easily from D sugars. What is the D sugar? The D sugar is the complete mirror image of this sugar, not just the mirror image at the configurational carbon. It's the complete mirror image. So notice I'm reflecting each of these centers . So this is the D version of the sugar. But if I want to draw the beta, I have to draw it in the haworth form or the ring form. And this is what I wanted to show you how to do quickly. So the point here is, if you're given an L and you're asked to draw a D, you would want to draw a complete mirror reflection, not just the center. There are lots of D sugars. This particular arrangement of OHs is a particular sugar. The D sugar is the complete mirror image. So if you were asked to draw the D, I would just draw the mirror image. Then what I would do is draw the haworth in this particular arrangement so that the oxygen is in the back left corner. Then what you want to do is set up the anomeric carbon. This carbon is the anomeric carbon, and it actually undergoes a carbonyl attack, and the carbonyl opens up, and that's why I presented this material. In other words, if I just had a big long chain and it had an OH, this should kind of make sense to you now, that this could attack this delta plus carbon, this could open up, and then after a proton exchange, you would have an OH group here. So this aldehyde up here becomes an OH group. If it is the beta anomer drawn in this manner, the OH is on the top. Okay, so this is the anomeric carbon. It's in the ring, it's the carbon attached to two oxygens. The H goes down. On these kind of side views of rings, right, this is up, this is down. All right, now, what you want to do is everything that's on the left, you want to put it on the top, and you want to fill in the ring in this direction, clockwise, okay? So I go to the next center, the OH is on the left, so I'm going to put it up. Anything on the left goes up. The hydrogen goes down. All right, then I go to the next carbon. Since the OH is on the right, the OH is down, the hydrogen is up. I go to the next carbon, okay? The OH is up, the hydrogen is down. What you're trying to do, this is the same as taking it and tipping it over. Now, here's the tricky part. This oxygen is this oxygen, okay, in the structure. This is the oxygen that becomes part of the ring. So the way this works, if you want to work out the stereochemistry, this had an OH down here. If you want to work out the stereochemistry, you have to envision this as a little tripod or as a tetrahedron. And what you have to do to form this ring structure is you have to rotate it so this O is in line with the other carbons that are part of the ring. So everything in the ring is supposed to be on the vertical. So what I would do is I would rotate this around in my head or on the paper. What you're trying to find out is where the CH2OH and the H are going to be. The CH2OH is going to be on the left, and the H is going to be on the right. So in the final structure, the CH2OH is going to be on the top, and the H is going to be on the bottom, like that. Now, what did I draw here? I drew the beta D sugar. Now, what if I asked you to draw the alpha L, okay? What if I wanted you to draw that? Well, you could go back to the L sugar I had drawn at the beginning, and you could loop it around the other way and draw the whole ring the opposite way. But what I recommend instead is recognizing that the L sugar is the mirror image of the D sugar. So if I wanted to draw the L, I would just draw the mirror image of this. And notice I'm really drawing a mirror image. I'm viewing the ring as though it's tilted up like this. This is in the front. This is in the back. Okay? So now realize I haven't fixed the alpha and beta aspect of this. I'm worried about my dog because I feel like he's doing something nefarious right now. Okay. Okay, so what I did here is I made the complete mirror reflection of this, but this is not, though this is the L, this is not the alpha. This is the beta. Why is it the beta? Because this is the anomeric carbon. How do I know it's the anomeric carbon? It has two oxygens attached to it, okay? And notice the whole ring is drawn as a reflection. Did I do that right? Yeah, I did that right. Okay, so if I want the alpha, what I have to do is put the OH on the bottom, okay? So with this kind of a drawing, if the OH is on the top, it's beta, and if the OH is on the bottom, it's alpha. So this is the alpha D. Now, if you wanted to draw the beta D, you would just put the OH up here. Notice from going from alpha to beta, you're just switching these two. But going from D to L is a complete mirror reflection, but not necessarily of this carbon. The anomeric carbon is in constant flux. It's always closing, opening and forming the straight form, and reclosing, almost like it's reclosing in the back. So the carbonyl is getting flipped in opposite directions depending on how it gets, depending on what's going on. And though these two are not in equilibrium with each other, these are completely different compounds, this is constantly in equilibrium with the alpha D. You know, opening and closing and reclosing the opposite way here. And it really is carbonyl chemistry. Okay, good. So that's our first issue. The other thing I wanted to go through, and as I said, I will type out some stuff. I'm going to type out an email to you tonight with some information about the test and things you should be focusing on again. Again, don't forget about the wittig, and you're going to see this in a synthesis that I'm going to do in a minute. The next thing I wanted to go over, was the reaction with thionyl chloride. This is called thionyl chloride. What reaction? The reaction of carboxylic acids with thionyl chloride. And I'm going to give you a superior mechanism to this because I wasn't happy with the mechanism I wrote in class. So I'm going to write a better mechanism. It's a little easier to follow. Okay, this reaction is critical to doing synthesis because it's an intermediate state that's needed to move between carboxylic acids and many derivatives. You can make lots of things from acid chlorides, as I've told you in class. Okay, so let's talk about this reaction. All right, so in class, the way I did the mechanism was that I focused on this oxygen, okay? These oxygens are not wildly different in a way, but I think we can write a nicer mechanism with this oxygen. Okay, so I'm following along with Loudon on this. I prefer his mechanism to the one I wrote in class, so I apologize. I wasn't real pleased with what I wrote. I got really bogged down with that hydrogen. But anyway, what do I want to do? I want to take this pair of electrons, I'm doing this kind of directly, and then pop these open. This is where the flip is going to occur, the initial flip. Then, what am I going to do? At this point, I have a sulfur, an O minus, and some of you that are getting good at doing these flips, this isn't that big a deal anymore. Okay, now in doing this, what's happened? Well, this now has a plus charge, but there's quite a bit of resonance here because this oxygen and this oxygen has lone pairs that can donate into that plus. And you guys should be able to draw that resonance. That's one bond resonance. One bond resonance. Okay, I'm not going to draw them all out. All right, then this is going to flip and kick this group off. Okay? What we're setting up to do here is we're setting up to lose SO2 gas and a chloride ion. All right, let's draw the result of that. You should have that little movie going in your head all the time, the little voice, my voice in your head saying over and over again, what do I do next? What's the result of that? Constantly saying that to yourself. Okay, so we said there's some resonance stabilization here. I hope I have the same number of carbons. I don't remember how many I had. Okay. This has a delta plus, a strong delta plus because there's a lot of positive charge on that carbon. Putting the sulfur on has made that carbon more what? Electrophilic or nucleophilic? Electrophilic. So the chloride that you spit out, now chloride isn't the greatest nucleophile, but this is going to be a fabulous leaving group. The chloride that I spit out is going to come in and take the place of the pi bond that we had. So now we've got, and there are different ways to write this. This is not the only way to write this mechanism. Okay? There are parts of mechanisms that really can be varied a bit. Okay, so we have this. Now what do we want to do? We want this to come off, okay, and this to snap off. In other words, what I'm making here is SO2. Why does this drive the reaction? Because SO2 is a gas. So as I always say in class, if the equilibrium favors the starting material, if one molecule forms SO2, the equilibrium will shift to form another molecule of SO2. So the leaving group that leaves is the best leaving group. And we've said that many times in class. Okay, so now what do we have? And by the way, if I lost a carbon here, I didn't mean to. Okay, so I just made SO2 gas, which is going to leave my reaction, plus a chloride ion. All right, now what do? Well, at this point, depending on how you're looking at this, sometimes people draw these electrons coming in right away. It doesn't matter. But depending on how you're looking at this, right, this has other resonance forms. So one resonance form, I really like this mechanism a lot better than what I wrote in class. I want to annihilate that mechanism. Okay, that's one of the resonance forms you would draw. And you could draw another one with this one if you wanted. Of course, the resonance form with the chloride is not as important because chloride, what's the reason? You guys know. What is it about the orbitals with chloride? We learned about this when we did aromatic chemistry. And then what I'd want to do is take my Cl- and pull this H off, okay? And then we would form the acid chloride. You might wonder, why don't you do these reactions with base around? Sometimes you're worried about the base actually attacking this species. Okay, so that is a much better mechanism, and I hope you will use that mechanism. And when I do my review, I'm going over this mechanism as well. Finally, I want to go over the synthesis that I did with a couple students in my class, and in my office today. So for the 2 students who did this, I apologize. It probably bears repeating. I feel this synthesis brings into play a lot of the really important chemistry that we've gone over in this last third of the course. So what I suggested to them is that they make this very strange looking molecule. Okay, from these little fragments. Okay, so from this aldehyde and this halide, okay, and I'm going to give you an alcohol, so it's 1, 2, 3, 4, 5, 6, a 6-carbon alcohol. Okay, so as we expand a little bit our notion of synthetic strategy, and a lot of you have come a long way. What you basically have to do here is you have to make 2 of these. These are not bonds. Maybe I shouldn't have done that. But you have to make 2 of these, okay? 2 equivalents of it. So we just have to make this, all right? And then somehow we've got to get this hooked onto this C. This piece is going to entail bringing these 2 pieces together. Okay, and there are several ways I can do it. And then hooking these pieces into this carbon, it has to be Grignard chemistry. Why? Because I'm attaching a carbon at a carbon that has an oxygen on it. And that usually is suggestive of doing Grignard chemistry, or at least it's consistent with Grignard chemistry. Now, what I want to focus on first is how I'm going to make those 2 pieces from these little ingredients that I've got. And there are several ways I could do it. So you guys could think about this, and I've got my structure memorized, so we'll be okay. What we have to do is think about the CC bond-forming reactions that we've learned. So we have to hook this carbon to make a 5-carbon chain. And you guys, you could think about Grignards to your heart's content. You could do a Grignard, or you could do an organolithium, but I'm going to do something different. And so what I'm going to use instead is the wittig. And this is the reaction I woefully neglected on my list of reactions that you had to go over. And I'm going to fix that tonight. Could we use a wittig? And if you're not good at the wittig, let's talk about how you do this. All right, to do a wittig, you have to make a wittig reagent. What do you make a wittig reagent? You have to make a phosphorus ylide. What do you make a phosphorus ylide from? You make it from a halide, just like you make a Grignard. So if I want to do a wittig, I'm going to do this forward. So one of my big strategies is just to make the 5-carbon piece. Now what's so great about a wittig? Wittigs are great because, right, this is triphenylphosphine, because you get a double bond out of them and you can modify the double bond. So I add triphenylphosphine, right, it attacks this carbon, kicks out the halide. Go over the wittig. I feel like people don't know it. That has a plus charge now, and then the counterion for this is bromine. All right, what do you have to do? You have to activate this so it'll become a nucleophile. To make it a nucleophile, you've got to treat it with base. Normally, in the laboratory, people have to use a very strong base like N-butyllithium. N-butyllithium pulls this proton off, and of course this is stabilized partially by the charge and partially by resonance stabilization. I've lost my eraser, hold on. Okay. So we get the wittig reagent. So this will go to form this anion and this charged phosphorus species. So this is the ylide. Okay, what do you do with the ylide? you take the ylide and you attack. So again, how do you make an ylide? You take a halide, you substitute it with the phosphorus reagent, and then you rip the hydrogen off of the NBO-lithium. When you get this, this is going to react with the aldehyde that I gave you as one of your starting materials. So you have an aldehyde. Okay, what happens? This attacks the carbon, the oxygen opens up, and it hits the phosphorus. Okay? Then what happens? Okay? We have what is called the oxaphosphatane. Now, it is controversial as to whether or not this forms directly, but this is kind of a standard way to draw it at this level. I showed you another intermediate in class that was called a betaine intermediate. This will collapse to form an alkene, and as we discussed in class, the alkene could be either cis or trans. Okay, so this could be this plus it's cis plus it's, this is the Z plus the E compound. Okay, that's very important because what that does is that constructs the two, this was our structure. Structure had a lot of symmetry. I'm almost done. Believe it or not, we are almost done. It seems like endless here, but we're almost done. 2, 4, 6. Okay, too many carbons. 1, 2, 3, 4, 5. There we go. This structure, okay, this constructs these two pieces of that structure. And what's great about this is it already has the functional group in it so that you can functionalize it so that you can do a Grignard. Okay, so here's the deal. How do I functionalize that to do the Grignard? All right, what I would do is I would take this structure and I want to make it a halide. So how do you easily make a halide? Just add HBr. And one of the products, not both of them, but one of the products will be this. Then all you need to do is add Mg and ether or lithium and hexane, and you will have the Grignard. Okay? Now, here's something we've been learning recently in class. You need to hook this Grignard onto this carbon 2 times. And one of the things we discussed in class is that if you do a traditional Grignard, which would be through an aldehyde, you would have to do the Grignard, oxidize it back up, and then do the Grignard again. And what we discussed in class is the fact that carboxylic acid derivatives are in a higher oxidation state than the typical Grignard, than an aldehyde or a ketone. Being in a higher oxidation state, you can do more substitutions on them. In other words, they typically flip. Okay, and because they flip, you can do a second attack. So let's talk about converting this into a carboxylic acid derivative so that I only have to do the Grignard in one pot. In other words, I can just add the Grignard twice to the same substrate. All right, so how would I do this? Well, I have a 6-carbon alcohol, which is roughly what I need, but I've got to convert it into a carboxylic acid. How do you convert a primary alcohol into a carboxylic acid? Well, typically you use some kind of strong oxidizing agent, for example, just to have a little variety because we've been using KMNO4 so much in class. You could use chromic acid. If you use chromic acid, you would make the carboxylic acid. Now, when you get to the carboxylic acid, it's in an enhanced oxidation state. It's in a +3 oxidation state, and it does have the capability to jump down 2 steps, but not with that hydrogen on it, okay? Or at least not initially with the hydrogen on it. So what do we do? What you want to do is convert it into an ester, all right? And you guys have many, many methods to convert it into esters, and I made a list of them during the review class. You can make esters using diazomethane. You can make esters using potassium carbonate and an alkyl halide. You can do the Fischer esterification. You could convert this into an acyl halide and add an alcohol. There's a whole bunch of ways to make esters. I'm going to use diazomethane. So if I wanted to convert this into an ester using diazomethane, I would add diazomethane, which looks like this. And sometimes when you look at your flashcards, it's written in a formula. It's written as a condensed formula, and sometimes people have trouble with that structure. What happens with diazomethane is it pulls the hydrogen off the carboxylic acid and makes the carboxylate anion, okay? This protonates the diazomethane. And now this carbon is a zero order carbon with a fantastic leaving group on it. What's the leaving group? Nitrogen gas. So this acts as a nucleophile, hits this carbon, and knocks the nitrogen gas out. Okay, that is a great way to add a methyl group onto an oxygen and get ready to do a double Grignard. Okay, so when I do this, I now have, go over that reaction. That is a good reaction. These are all on the flashcards, and there are many, many examples on the flashcards. So rather than start with an aldehyde, which I could do, you could do that, I'm going to start with a methyl ester. All right, what happens with my Grignard? I put these together, add them together. The Grignard is going to attack this carbonyl. I'm just going to kind of trace you through this. These electrons are going to go up. Okay, then what happens? These are going to flip down. So this is 1, 1. This is 2, 2. In other words, this is the second step. I'm just abbreviating a little bit here for time's sake. What do I end up with? I've hooked one of my two groups onto the carbonyl. Now again, what's so great about an ester? It flips. Because it flips, you end up with a carbonyl, and you can do another reduction. Now what's going to happen here? Stick or flip? This is a stick. The reason I chose the synthesis from among the syntheses I did in my office today was I just felt it really captured the spirit of all the things we've been doing recently, and it encompassed a lot of the chemistry that we've been doing. Okay? So then we get this thing, it looks sort of like a bird or a bat or something. Maybe like a Star Wars